I'm Professor Brad Fulton, and welcome to my Stats podcast. This is an edited audio recording of my course. Each lecture is its own episode, and there's a total of 24 lectures. This course provides an introduction to the quantitative methods social scientists and data analysts use to collect and evaluate empirical data about society. Through this course, you will learn to gather, describe, and analyze data with an emphasis on the application and interpretation of these methods. This course will also help you to be a more informed and critical reader of academic research, public opinion polling, and advertisement claims that present statistical evidence. Although some of the current events I reference might be dated, the content is timeless. I hope you enjoy this lecture, and if you have any questions, you can email me at bradrfulton@gmail.com. Hi, my name is Professor Fulton. If you like this podcast, you'll love the book I use for the course. It's titled Statistics, Unlocking the Power of Data. This book uses a highly intuitive approach to help students visualize statistical concepts, which accelerates understanding. I've reviewed dozens of textbooks, and Unlocking the Power of Data is hands down the best one out there, mainly because of its unique intuitive approach and straightforward explanations. You can find a link to the textbook in the show notes, and if you use the promo code BLOCK5, you'll get a 10% discount. So I'm impressed with you guys. This is not easy stuff. The pace is crazy. I don't know if you guys feel it, but it's sort of like every day there's a new thing. You're just barely getting your mind around the thing that we covered the day before, and it's like, okay, now let's do this. And that's one of the drawbacks to summer session is it just keeps coming. So it's like double days in some regards. But looking at the assignments, you guys are doing well. You're getting it. I can tell which parts are more challenging than others, and that's understandable. But I think you're doing a good job of making the attempts to do it, both part 1 and part 2, and you're learning. So did you have any specific questions about the assignment?
Question 1 of part 2.
Oh, question 1 of part 2. Remind me.
Percentile method.
Okay. We didn't get to cover that in class. It was in the lecture, and I'm going to go through that right after this so we can do that. Any other questions? Question C was, what do you expect the shape and the center of the bootstrap distribution to be? It's kind of like, how do I figure that out? But earlier in the chapter it says all sampling distributions and all bootstrap sampling distributions will be generally bell-shaped curve and symmetric centered around the mean. And so when I sat there first, I was like, okay, how do you do this? Like, do I use stat key? Is there a formula? Oh, wait, no. All of them are like this. So, and that's sort of what that question is testing. As you guys work through these problems more, you'll begin to see, okay, this one can just be answered intuitively or visually. And especially like on the exam, you're not going to have a computer. So you're going to know that it either is a formula or just visually looking at it. To go over just quickly part 2 from the day before, the correlation score. Looking at the examples that you guys picked, a lot of you picked variables that weren't really quantitative variables, and so it said there's no correlation, or I think some of you would get correlation of 1, and so you would basically never get a correlation of 1 unless you're comparing the same thing. And so I think maybe Chris had an example where it was gen temp. What he found was that variable X was strongly correlated with variable X, meaning if you compare 2 variables to each other, the correlation will be 1. As one goes up, the other one's going to go up. Anyways, in interpreting correlation scores, just so that you guys can have an example that works, here's 2 variables that you can use, edu and conInc. And conInc is the best income variable to use because it's a continuous variable. It's not chopped up into below poverty line, above poverty line, so that you can have an example that works. Similar to like how I set up part 2 for today's assignment, I gave you the variables so that it just made it easier, and then you could see the mechanics of it, of how it's supposed to work. With this one, the correlation between edu and conInc is 0.39. So what does 0.39 mean? What type of correlation is that? A positive correlation. So this is the proper way to interpret a correlation. Education and income are positively correlated. An increase in education level is associated with an increase in income level. And likewise, a decrease in education level is associated with a decrease in income level. Just to say education and income are positively correlated, that's a raw fact. And then the interpretation is, as a person's education level goes up, their income level is probably going to go up. Or if you find a person with a really low education level, it's a good chance that they're going to have a low income level. So when I ask for interpreting the correlation, it's putting into your own words or the real world experience of what that's saying. So remember the example a couple days ago about Obama's approval rating? It was the Gallup survey of 1,500 Americans. 49% of these people approved of the job Barack Obama is doing as president. And so our sample proportion is 0.49. A question that's been coming up a lot is calculate a 95% confidence interval for the point estimate, which is 0.49. So a lot of times you're given a sample statistic and you're asked, what's the population parameter? And the only information that we have and our best estimate of the population parameter is our sample statistic. But it's only an estimate, and so we want to know what's the confidence interval for that estimate. And there's two ways to calculate a 95% confidence interval. And I'm going to walk you guys through both of those ways. So the first is calculating the 95% confidence interval using the standard error method. And so what we do is go to stat key. What type of variable is this?
Is it the one binary categorical variable?
Yep, categorical variable. So we go, it's a single proportion, so we click on that. And then we go up here to edit data to put in what our study was doing. And so the count would be, there was 735 that said they approved of Obama, and then the total sample was 1,500. So we plug in those two numbers, we hit OK. So then we have our original sample up here, and then basically we want to know how the sample statistic of 0.49 varies from sample to sample. And so that's where we do the bootstrapping to generate multiple bootstrap samples, which will give us multiple bootstrap sample statistics. So we're going to do that 1,000 times. This gives us our bootstrap sampling distribution. With the standard error method, the two values that we need is the sample statistic and the standard deviation of the sampling distribution. That is right up here. So we can take this information, our sample statistic, which is 0.49, and then the standard deviation of the sampling distribution, which is also called what?
Standard error.
Standard error. You guys are good. You're on it. 95% confidence interval equals our observed sample proportion plus or minus 2 times the standard error. Observed sample proportion is up here. Standard error is right here. And we plug in the numbers. Now, here's what's interesting. So here's our observed sample proportion, and then the confidence interval is plus or minus 0.026. Now, remember in the Gallup study, they said that the margin of error was plus or minus 0.03. That's how they got that value, was by doing this equation, and they just rounded up. So the way that Gallup figured out what their margin of error was is they did exactly this. So there's some relationship between what Gallup does and what we're doing right here. Then our confidence interval is 0.464 to 0.516. And the proper way to notate confidence interval is put the low number on the left side and the high number in the range on the right side. So this is important. Probably in exams or whatever, I'm going to ask, what's the answer? And then what's the interpretation of the answer? And so here's a way of stating it. We are 95% confident that the true percentage of all Americans that approve of Obama's job performance is between 46.4% and 51.6%. So we want to know what your answer means. Okay, so now the second way of doing it would be calculating the 95% confidence interval using the percentile method. We can go back to our bootstrap sampling distribution. And two-tail is, this will come up later where we explain what the difference between left tail, two-tail, and right tail. But two-tail gives you the 95% of the values in the middle of the distribution. It determines where 95% of the values lie, and then it gives you the endpoints, the bounds of that 95%. And so then down here gives you the low end of the confidence interval and then the high end of the confidence interval. The way to calculate the 95% confidence interval using the percentile method is by using stat key, or you could sort of visually say, what's the 95% confidence interval? And you say, where do 95% of the middle values fit? And you give an estimate. The stat key does it for us. And we notice that the low end of the confidence interval is 0.464 and the high end is 0.516. And so it gives you the same answer because it's more or less calculating the same thing, but doing it in different directions. Then the interpretation is still the same. We're 95% confident that the true percentage of all Americans that approve of Obama's job performance is between 46.4 and 51.6. We're moving on to the core. I think we can say this is the core of statistics. It's hypothesis testing. So the scientific method is basically you have a hypothesis and you want to test that hypothesis to see if it's true. And so in social science, you also have a hypothesis and you want to test to see if that hypothesis is true. But instead of using data from the natural world, we use data from the social world. But it's the same process as you would use in biology or chemistry, but it's just now applied to the social world. The question that is going to be asked when you're doing hypothesis testing is, what is the probability that our observed outcome could have occurred by random chance? We see a relationship or a pattern, and we want to know what's the probability that this would just happen by random chance? That it's actually what we think is a trend really could have easily just happened by random chance. And so that's a question that we'll be asking throughout this process of hypothesis testing. I'm just going to walk through the whole process with one example, but hopefully by doing a real-world example interplayed with the technical terms, it might make it more intuitive. So just like you guys will have for your final research project, you'll have a research question. Our research question today is, do male students spend more time exercising than female students? Let's say we're working with a population of Duke students. The first step, before we can even begin to answer the question, we need to collect data. So I've collected the data on 50 students. Our sample size is 50 students. Our population is all of Duke students. And so then the two variables that I gathered information on was, for each student I said, what is your gender and what is the number of hours spent exercising last week? What kind of variable is gender? Categorical. And then what kind of variable is number of hours spent exercising last week? Quantitative. Very good. So then what we've already done is our sample statistics. So once we have our data, we want to do the describing our data, and that's where sample statistics come in. Can someone interpret this sample statistic? P hat sub m.
Proportion of males in the study?
Yes. It's the sample proportion of males in the study. And then P hat F would be the sample proportion of females in the study. This example that I'm going to be walking you through is almost a review of everything that we've covered up until this point. We started off with sampling, doing a random sample of a population of interest, and then we were talking about variables, different types of variables, quantitative variables, categorical variables, and then we did a lecture on describing the data, the exploratory data analysis. This next one is the number of hours spent exercising.
Sample mean of how many hours everyone works?
Exercise, yep, a week. So what are other sample statistics that we could gather from this quantitative variable? What are other sample statistics? So sample statistics is a general term that is things that you can draw from your sample. With categorical variables, there's less that you can draw. You can really only get the proportion. But with quantitative variables, because they're quantitative, you can do a lot more analysis of it. Like you said, you can get the median, you can get the standard deviation. And so when we're asking for sample statistic, it isn't just mean or proportion, but it's any type of statistic that we can calculate from the data. So keep that in mind, that sample statistics can be a lot of different things. an example would be a sample statistic of two quantitative variables would be the sample correlation value. So remember when we calculated correlation between two quantitative variables? That's a sample statistic because it's a value that we're generating from our sample. Another sample statistic that we could pull from our data would be x bar m and x bar f. So what this is the sample mean number of hours male students spend exercising, and x bar f would be the sample mean number of hours female students spend exercising. So this is another sample statistic that we could pull from our sample data. The way that you would calculate is you have your data, and right now you have row 1 is person 1, and we find out male, and they spend, let's say, 10 hours a week exercising. Row 2 is female, and they spend 12 hours. So the way that you would calculate this value is you would separate all of the female people out and then add up all their exercise scores and then divide by the number of females, and then you do the same for males. Okay, so then the last sample statistic that we're going to look at for this example is x bar m minus x bar f equals 3 hours. And that's the difference in sample means. Why would we be interested in this particular sample statistic?
That explains who spends more time.
Yeah. How so? How does it explain who spends more time?
The male spends 12, but the women have more people.
Okay. So the women have more people.
That's what I was going to say.
Okay. So Tim brings up a great point. There's more women in the sample. How would the number of women versus the number of men affect the mean value? Think about it. If you have 30 women in this sample, and you're going to look at their time spent exercising for each woman, and you're going to add those up, but then you're going to divide by what to get the mean number of hours? 30. Yep. By dividing by the number of people, we'll equalize. Basically, Tim's concern doesn't need to be a concern because we're looking at the average. And so whether you have 100 people or 1,000 people, the average is still going to be the average of the whole group. And it doesn't matter if you have 10 people or 100 people. So going back to this, why is this sample statistic, why would we be interested in this in light of our research question? I think you had said it, Chelsea. On average, male students appear to spend more time exercising than female students. In fact, on average, 3 hours more. You'll always find some men who exercise very little and some women who exercise a lot, but on average, men exercise more than females. But like we've looked at before, this is just a sample statistic. What we're interested in is our entire population of Duke students, because we want to know, of all Duke students, do male students spend more time exercising than female students? What this provides, this 3 hours, provides a point estimate. We're saying, well, what's the population parameter? What's the difference in the amount of time spent exercising? Our best estimate is that men spend 3 more hours exercising than women.
So 3 hours is like the point estimate?
Yes. It's our point estimate, and it's based off of our sample statistic. So at least here's one example where there's consistency in terms. So for each of these sample statistics, they will provide us a point estimate for our population parameter. So if we wanted to know also from this data, what's our point estimate for the population proportion of females at Duke? What's our best estimate at the proportion of female students at Duke? Brittany?
40% or 0.4?
Female students.
Oh, 0.6.
0.6, yep. And likewise, if we wanted to know the population parameter for the mean number of hours spent exercising a week, what would be that point estimate? We take the sample mean, and so that is our point estimate for the population parameter. So at least in this scenario, there's nothing new. The only thing that's new is I'm introducing new sample statistics, but they all function the same way. So whether it's just a proportion or a mean, they function the same way as a sample mean of a subset of people or even if you look at the difference in sample means between two people. It's all sort of working the same. This is the data. Everything that we've covered in class is right here and it's already addressed. We've already done this. So then what we're going to do is transition to hypothesis testing. I'll forewarn you, it has terminology again that you never use in everyday life. So it's just a matter of mapping it out as Tim describes, just sequentially, what am I talking about, and creating categories for the different things. And so hopefully these slides, what I've attempted to do is distill everything in the textbook into a nice sequential order. Based on our sample statistic, we think, yes, male students spend more time exercising than female students. That's based on our sample statistic, but we know there's variation in our sample statistic, and so this is where hypothesis testing comes in to see if our hypothesis is true. So we start with the null hypothesis, and this is every research project, every study that you'll ever do, that you'll ever read, you always need to identify what's the null hypothesis. In the null hypothesis, it's notated in this way, H with a little sub-zero. So whenever you see that, translate in your mind null hypothesis. And what the null hypothesis is, it's the claim that there is no effect or no difference. So the null hypothesis, and probably why it has the word null, means none, that there actually is nothing special going on. There's no difference, no effect. And so, in a sense, for our example here, the null hypothesis is the claim that time spent exercising does not differ by gender. So it's almost the antithesis of what you're studying, a hypothesis that there is no effect. And then the other hypothesis, don't worry, there's only two hypotheses that you need for any of these studies, is what's called the alternative hypothesis. And it's notated as H sub A. So whenever you see H sub A, think alternative hypothesis. And the alternative hypothesis is the claim that we seek evidence for, usually that there's some effect or difference. So the alternative hypothesis is actually the hypothesis that we're interested in. It's the claim that we're looking for evidence for, that there's some difference or some effect. So for our example here, it's the claim that male students spend more time exercising than female students. In a sense, the null hypothesis is imagining a world where there is no difference, there is no effect between the two things that you're measuring. The alternative hypothesis is you coming along and saying, no, I think that male students spend more time exercising than female students. And I'm going to gather some data, some evidence to prove my hypothesis. Again, our research question is, do male students spend more time exercising than female students? The null hypothesis is the claim that there is no effect or no difference. Basically that the time spent exercising doesn't differ by gender. If you're going to put into your own words, what would be our null hypothesis for this study? Because I'll ask you to write out in words what the null hypothesis is, and then also write out in numbers what the null hypothesis is. And there isn't any one right way to state this, but it needs to be within the range. Yes?
Male students do not spend more time exercising than female students.
Perfect. You start by looking at your research question, your claim, and you say, well, let's switch it up such that the difference that we're looking for actually doesn't exist. So as Chris said, and another way of saying it is, time spent exercising does not differ by gender. Or as Chris said, male students do not exercise any more than female students. This is the word way, in words stating the null hypothesis. And then the numeric way or the equation way would be this. So can anyone interpret what mu means?
Population.
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 Population mean. Good. I should let you guys collectively do the exam. 'Cause then you could, So when we're talking about hypotheses, we're always talking at the level of the population. That's why we use this notation of the population parameter, the population mean. So then what is this equation saying?
The means, the exact same.
The mean,
Of exercising?
yes. So the population mean number of hours that men spend exercising equals the population mean number of hours spent exercising females spend exercising. This is saying the same thing as this. And another way of looking at it would be that the population mean number of hours exercising for men minus the population mean number of hours exercising for women would equal 0. Does anyone see something here that looks familiar from one of our sample statistics?
There's 3 hours with the X sample mean males minus sample mean females.
Uh-huh.
There's 3 hours.
Yes. There's a reason why we calculated that statistic, and that was a point estimate for the population parameter. And so we want to know what's the probability of getting the outcome of 3. I'll walk through it more. But
Is there a name for that?
it's called sample difference in means. The sample difference in the alternative hypothesis is the claim that we seek evidence for. The hypothesis that we're interested in proving. So can someone take a stab in words what our alternative hypothesis would be?
Male students spend more time exercising than females.
Perfect. Male students spend more time exercising than female students. So it might seem like mundane, it's like, oh, don't we just go through this? But every research question or study, I'm going to be asking you, what's the null hypothesis? What's the alternative hypothesis? And you need to be able to nail it because that sets up everything for the hypothesis testing. So we have the word form and the equation form. Can someone interpret this right here? Rachel or McKay?
You're saying the population mean
Mm-hmm.
of males is greater than the population mean of females.
Uh-huh. And it's the mean of, what are we measuring? Mean number of hours. Yeah. You can rewrite this equation this way, and that shows up again similar to our sample difference in mean. So this is how we form the hypothesis. So I have my hypothesis. The only way that I can really test my hypothesis is with evidence. And so the evidence, what is my evidence that I'm working with? It's based on, I had to go collect data. And so I did a random sample of 50 students. So that's my evidence. It's just like in a court case, if you have a theory that this person is guilty, in order to convince the jury, you need to gather evidence. And what social scientists do, the evidence that we typically gather is data. So in order to test my hypothesis, I needed to go gather evidence. And so that was my sample. I gathered data on a sample of 50 students. The alternative hypothesis is supported by finding evidence, otherwise known as data, that both contradicts the null hypothesis and supports the alternative hypothesis. So my evidence needs to contradict the null hypothesis. Can someone restate what the null hypothesis is?
The claim that there's no effect.
Yes. So the data that I gather, in particular the sample statistic of the mean number of hours that men spend exercising and the mean number of hours that women spend exercising, my evidence needs to show that they're not equal. Yes?
Since the null hypothesis and alternative hypothesis contradict each other to begin with, wouldn't any evidence to support the alternative hypothesis automatically contradict?
Uh-huh. That's a very good point. So the null hypothesis and the alternative hypothesis have to be mutually exclusive. What Brittany was saying is that if the null hypothesis is true, then the alternative hypothesis can't be true, and vice versa. But the difference that I'll say, Brittany, is that even if we have evidence that shows that the null hypothesis is not true, we want to know how strong is the evidence that our alternative hypothesis is true.
Okay.
So again, maybe in a court case, you have, beyond a reasonable doubt. So we might have evidence for the alternative hypothesis, but it's really weak evidence. Now this is a tricky part in the process. I still have a hard time getting my mind around it, but again, as we do examples, you'll begin to see at least how it works. We need to look at the strength of evidence. So we assess the strength of evidence by assuming the null hypothesis is true. It's a process for doing a hypothesis test, and it's the way that you set up this study, is that you assume the null hypothesis is true. Another way of thinking about it is that you imagine that we live in a world where the null hypothesis is true, that there is no difference by gender in the amount of time spent exercising. And then we determine the probability of seeing an outcome as extreme as the outcome in our observed sample. This is where it gets confusing because I'm almost sort of talking about imagining another world. So we start by assuming the null hypothesis is true, a world in which the mean number of hours spent exercising doesn't differ by males or females. And then we determine the probability of seeing an outcome that's as extreme as the outcome in the observed sample if the null hypothesis is true. So it's a formal way of looking at it. So then to see if a sample statistic, and what's the sample statistic that we're using for this study? The difference in sample means, the sample statistic. So does that provide evidence that both contradicts the null hypothesis and supports the alternative hypothesis? We need to know what kind of sample statistics we would observe just by random chance if the null hypothesis was true. So I'm getting deeper and deeper into complexity, but stay with me because we're going to emerge back out with a real life example. But you guys got to know the general approach to testing hypotheses with evidence. So basically, we need to know what kind of sample statistics we would observe just by random chance if the null hypothesis was true. So the thing that we're going to be testing is we have our observed sample statistic, which is the mean number of hours spent studying by males minus the mean number of hours spent exercising by females. And our sample statistic is 3 hours. And it's also referred to as the difference in sample means. The question is, how unusual would it be to observe this sample statistic by random chance if the null hypothesis was true? To go out and randomly sample 50 people, ask them how much time they spend exercising, and then calculate the sample statistic. How unusual would it be to get a sample statistic of 3 hours? Can someone try and rephrase this question? You want to try, Brittany?
So like the null hypothesis says that there's no difference. You're like creating a world where that would be the mean, and then you're trying to figure out if 3 hours, which is what we actually observed, is something that could just randomly.
Yeah.
How likely it is that that would occur in that scenario?
Yeah. One of you had asked a question like, well, what if we just randomly happened to gather 90 women in our sample? And I'm like, okay, well, that could happen, but what's the likelihood if we had a population where there's the same number of men and women, and we did a random sample of 100, and 90 of the people in our sample were females? I think maybe it's Brittany who asked the question, and she's like, well, what if that happens? And then my response was, well, what's the likelihood, or how unusual is it that that would happen? So that's the same thing. It's like, if our world is such that there's no difference, what's the likelihood that we would actually find a difference as big as 3 hours? Another way of stating this is, what is the probability that we would observe by random chance a difference in sample means as large as 3 hours if male and female students did not differ in the amount of time they spent exercising? There's always a chance that you could get a very strange sample or an unusual sample, but you kind of want to know, well, what's the probability of getting that type of sample? To answer this question, we need a distribution of sample statistics that would occur if the null hypothesis was true. We need to run a simulated study where we create a world where men and women don't differ in the amount of time they spend exercising, and then draw a sample of 50 people from that world and look at the sample statistic. And then we need to do that 1,000 times to see how much that sample statistic varies. So we'll keep walking through. This is, well, at least for me, is one of the most excruciating parts of statistics, because you're like, all these moving pieces are going on, but hopefully we can keep walking through. We can generate these sample statistics using the randomization process. How many have heard that term before or read that term? Okay, so the randomization process, it's in your textbook. There's two little things that we're going to be learning in this class that we use StatKey with. The first one was bootstrapping, and the other one is going to be this thing called randomization process. So for this course, it's important to know bootstrapping and then also randomization. It's good that you guys haven't heard of it, because I'm going to walk you through what it is that it's doing. So we're still working with the exercise and gender study, and we're going to talk about the randomization process. The sample size of our observed sample is 50. 30 females, 20 males. That's the information that we have data on. And for each of them, we have the number of hours they spent exercising in the last week. So imagine having 50 pieces of paper, and on each piece of paper is a number which corresponds with one of the values of X, which is the number of hours spent exercising in the observed sample. So the idea would be on each piece of paper, we'd write down one of the values for the number of hours spent exercising. And we get those numbers from this sample of 50. So we're basically taking our data set and just writing it down on each piece of paper. The way it works is you take the variable that you're interested in, and in this one it's the number of hours spent exercising, and we're going to have 50 values for that, one for every person. So we have 50 pieces of paper, and on each piece of paper is the number which corresponds to one of the responses that a person gave. We want to generate samples where the null hypothesis is true. To do this, we can randomly assign a gender value to each piece of paper. And if it doesn't matter, if the amount of time exercising doesn't differ by gender, we can just randomly assign female to the piece of paper or male. Because in the world that we're creating, the amount of time exercising doesn't matter.
Do those values have to match the actual? Like, would you randomly assign 30 of them to be female and 20 of them to be male?
Yes. Hey, look at that. To be consistent with our observed sample, we randomly label 30 pieces female and 20 pieces male. So that's really important because you need to keep the proportions correct. We would label 30 of them female and 20 of them male, and then we'd have a new data set that is reflective of this null hypothesis, a world in which the amount of time exercising doesn't differ by gender. And so we have this new sample that we've constructed through the randomization process. And the thing that we do with any sample is calculate the sample statistic for this randomization sample. So we're going to calculate the difference in sample means for this sample that we just created. Having just one sample statistic isn't enough. We need to have 1,000 sample statistics to see how much variation there is in the sample statistic. So just like in the bootstrapping, we would repeat this process 1,000 times to obtain 1,000 randomization sample statistics, which form a randomization sampling distribution, which is what Chelsea mentioned at the very beginning. But if I just said, okay, now let's take the randomization sampling distribution and calculate whatever, you guys would be like, where did randomization sampling distribution come from? Hopefully, this will help you to see step by step how we actually get the randomization sampling distribution. Now we get to go to StatKey to do this in reality, to run the experiment. So this column is all bootstrapping, and then this column is our randomization hypothesis test. So we're doing a randomization hypothesis test, and what is it that we're doing a test on? Difference in mean. So you click on that, okay, and then I said that this data has been collected, and it's actually right in here, and you guys would have it on yours. So you go down to male, female exercise hours per week. And just to show you the data, we have two variables. We have the categorical variable, which you guys identified, which is gender, and so it's FFF all the way down. And then the next column is the quantitative variable, and it just notates the number of hours they spent exercising. So there it is in spreadsheet form. Here it is plotted out. You see right here is female, and the sample mean is 9.4, and then here's all the males, and the sample mean is 12.4. So that's our sample, and our sample statistic, the one that we're interested in, is 3. It's 12.4 minus 9.4. So then to do the randomization sample, we take all of these values, the quantitative variable, the number of hours spent exercising, and then we're going to randomly assign the gender value to those scores. And that's what StatKey does, is it takes this column and just randomly assigns, and it's using that random number generator or whatever. Like, we don't have to say, okay, let's put this one here and this one here. It just does it randomly. So what we're going to do is we'll generate one sample, just so you can see. It generated one sample randomly, and what it is it's generating a sample in which the null hypothesis is true, where gender doesn't matter. The sample statistic that they get, which is the difference in sample means, is 2.167. So what does each dot represent in this dot plot? It represents one group of 50 people, and what is each value? It's the sample difference in means, the sample statistic that we're interested in. And so what this does is it generates a randomization sampling distribution. Our goal is to see where our observed sample statistic lies in the randomization sampling distribution, and to assess how unusual it would be to obtain a sample statistic by random chance if the null hypothesis was true. So basically, what we're wondering, going back, is the sample statistic that we had was that the number of hours spent exercising differed by 3 hours. And so how unusual of a sample statistic is that? So here's our randomization, and so then this is where we do 2 tail again, because that's going to give you the 95%. And so does the value of 3 fit within the 95%? I'm going to type in the value of 3. What that's saying is that there's an 11% chance that we would get this value just by random chance. So let me pull back out. And you guys can read up on what p-value is, but p-value is basically the formal way of saying what's the probability of getting this value by random chance. So you guys did it.